These are the practice problems for Lesson 8. In the first problem, they give you 4 different pairs of angles and ask you whether or not these triangles are similar. And to have triangles be similar, you just need 2 of the angles to be congruent. That forces the third angle to be congruent because remember, they have to add to 180 degrees. So A and B, they give you the same exact angles, 2 angles. So these 2 triangles would be similar because you only need those 2 angles to have similar triangles. C and D, they give you 90 and 37 and then 90 and 53. Well, the difference between 90 and 37 is this 53 degrees, and the difference between, or what you need to add to 180 degrees, and what you need to add to 180 degrees given 90 and 53 degrees is that 37 degrees. So that tells you that all 3 angles are congruent. They all have the same measure of degrees. So they are similar triangles. E and F, this is angle 65 degrees and 45 degrees. You need 72 degrees to complete the 180 degrees. For F, it's 14 and 71. You would need another 95 degrees to get to 180 degrees. So none of these 3 angles, 63, 45, 72, match these 3 angles, 14, 71, and 95. So they are not similar triangles. No congruent angles. And the last one, they give you a measure of 121 degrees and a measure of 70 degrees. Well, to have similar figures, all 3 angles have to be congruent. So that means that you would have to have 121 degrees, 70 degrees, and some third angle. And in this case, you'd have to have 70 degrees, 121 degrees, and a third angle. Well, 121 plus 70 degrees equals 191 degrees. So it's not possible. You're already past that 180 degrees. So G and H cannot be similar triangles. Okay, the next problem says draw 2 equilateral triangles that are not congruent. All right, so different sizes. So what I did is I drew a circle here, and I made one of the equilateral triangles, the word is inscribed. It's drawn inside that circle. Then I made another equilateral triangle that's actually outside the circle. So these 2 circles have the same radius, they're the same. So that makes this triangle different from this triangle. So they are not congruent. All right. But then if you look at all the angles, all 3 angles of an equilateral triangle are always 60 degrees. So 60 degrees, 60 degrees, 60 degrees, 60, 60, 60. And so that tells you that these 2 triangles, although not congruent, they are similar triangles because they have a scale factor that will take it from this triangle to this triangle. So the sides are related by a scale factor. So what I did is I took this length here, which is the radius of the circle, and I moved it over here. It's the radius of that same circle, but now the longer length is the length for the larger triangle. So that would be the scale factor. How much longer is this length? Well, it turns out that the scale factor is about 25 or about 1/4 larger. So the scale factor would be about 1 in 25 hundredths or 1 in 1/4 to go from this triangle to this triangle. So although not congruent, not exactly the same, they are similar. And actually every equilateral triangle is similar because they have the same size angles, 60 degrees. All right, explain why triangle ABC is similar to triangle ADE, and it tells you that these lines are parallel, BC and DE. So BC is parallel to DE. So whenever you see that, it's a hint to you to think about translating angles or looking for vertical angles or looking for alternate interior angles, something that will prove that this triangle is similar to this triangle. And so we could think of it, first of all, just as a dilation going from, this is the center of dilation. So if we take this triangle and translate it, it's 3 times. So the scale factor is 3 to get to B. The scale factor is 3 to go from B to C compared to D to E. But this is actually the one that would be dilated. The scale factor is 3 to go from AE to AC. And so this angle here, this line is parallel to this line. So this angle is, you could just translate it down here and show that this angle is congruent to this angle. But I like showing that it's a vertical angle. So you go through the intersection on the other side, that's a vertical angle, and then you can take this angle and rotate it 180 degrees. So you rotate 180 degrees, it's going to end up here, and those are called alternate interior angles. So now we have 2 angles that are congruent. This first one down here is shared by both triangles, so it's the same angle, so it has to be congruent. And then this angle is congruent with this angle, so these 2 triangles are similar. And you can prove it by looking at the third angle. This is a vertical angle. Now take this angle and rotate it 180 degrees. It's going to land right there. And so these are, again, alternate interior angles, so they are congruent. And so the smaller triangle is similar, or the larger triangle, I should say, is similar to the smaller triangle. Vertical angle, alternate interior angle, vertical angle, alternate interior angle. And so these angles are congruent, these angles are congruent, and this angle is congruent because it's the same angle. This shows the movement of the rotation. So you're rotating this around to end up right here, rotating this around to end up right here. All right, the last problem. No, actually, it's problem number 4 or 5. So it says, which of the following is true? So you're given 4 choices, and it tells you that this parallelogram is the beginning parallelogram, so it's PQRS, and that there's another parallelogram that's a dilation of this parallelogram with a scale factor of 3. It tells you that the center of dilation is point O, but it doesn't show you where that is. Well, I scaled this anyway. I scaled it using Q as the center of dilation. It doesn't really matter. You can use anything as the center of dilation. And that tells me that, so PQRS is 3 times PQRS is going to get you to PQRS prime for each of those. And so the first choice is P prime Q prime equal to PQ. Well, no, it's not. This is the length of PQ, and P prime Q prime is 3 times longer, so they're not equal. B is actually the correct choice. I'll come back to that in a second. C says is PQ equal to 3 times P prime Q prime. Well, if you took 3 times P prime Q prime, you're going to end up with a very long side. So actually PQ is 1/3 the length of P prime Q prime, because it gets smaller as you go from P prime Q prime to PQ. And it can be determined, and the choice D is cannot be determined, but it can. So we go back to B. The B choice is P prime Q prime is 3 times PQ. So if you take line PQ and it gets scaled up 3 times, so scale factor is 3 times this length, you get P prime Q prime. So P prime Q prime is equal to 3 times PQ. So P prime Q prime is equal to 3 times the length of, I put that up there for the length of PQ. So the correct answer is B. And the last one, the directions say, describe a sequence of transformations for which quadrilateral P is the image of quadrilateral Q. So you're going to take quadrilateral Q to quadrilateral P through a sequence, more than one transformation. Well, one way to do that is just to translate this so that A Point A lines up with A prime. I just labeled these that way. It's not given to you in the problem. And then you can see that this is a 90-degree rotation. You're going to take this length right here and you're going to rotate it 90 degrees and it's going to end up right there. So it's a 90-degree rotation in a counterclockwise direction, going from here up to here. So it's 90-degree rotation. So that's going to take that image up there. So translation, the translation was up 5 units and to the left 3 units. So 1, 2, 3, 4, 5. 1, 2, 3. If you're going to describe this, you would say that each point for quadrilateral Q is moved up 5 units and to the left 3 units. And then quadrilateral Q after that translation is then rotated with the center of rotation at A prime, rotated 90 degrees around this way. So the sequence of transformations is the translation and the rotation. So these are practice problems for lesson 8.